We're now going to talk about roll stability. And we're going to look at an airplane here from the back. So here's, we're looking from the back of the airplane, and I'll draw the horizontal and vertical tail back here to remind us that. But if we put our thumb into the page here, that's with our thumb going out the nose of the aircraft. A positive bank angle relative to the horizontal is defined as a right wing down. Okay, and a positive rolling moment with our thumb out the nose is in that direction. Okay, so positive rolling moment, positive bank angle. Now, before we go on, I'd like to remind us that we've already talked about pitch stability and yaw stability. And pitch stability is defined, or an aircraft that is stable in pitch requires that Cm alpha is less than 0. And an aircraft that is stable in yaw requires that Cn beta is greater than 0. Okay, and we've covered that in previous lectures. But what I want to point out about these two is that they are both dependent on aerodynamic angles. So this is so our aerodynamic angles are alpha and beta, okay? And roll stability, simply defined, is that when the aircraft gets some disturbance in roll or bank angle, we want the aircraft to correct. So, for example, if the aircraft here were trimmed at steady level flight with wings level, and it hit some turbulence or some disturbance that that banked the aircraft a little bit, so we have a positive phi or positive bank angle, we want the aircraft to correct and return to steady level flight. Okay, that's the definition of roll stability, or at least if it's stable in roll, that means that it will correct and return it to steady level flight. Well, so I guess, in a broad sense, what we want then is that some change in or the change in let me back up here. So the change in rolling moment with respect to phi needs to be negative, right? Less than 0. So if we have a positive change in phi, we want the aircraft to create a negative rolling moment to correct for that, okay? Now the problem with this, and the reason it's different than both pitch stability and yaw stability, is that a bank angle doesn't have any direct effect on the rolling moment or on the aerodynamic rolling moment of the aircraft, okay? And by direct effect, what I mean is that the rolling moment is actually a function of alpha and beta, the aerodynamic angles. It's actually not directly a function of bank angle. So if you think about an aircraft and the forces and moments on that aircraft, the aerodynamic forces and moments, those actually do not depend on bank angle. They depend simply on the velocity of the aircraft relative to the surrounding air. And the way that we define that is through these aerodynamic angles, alpha and beta. So let me draw a top-down view of the aircraft here. And so just remember, this is X out the nose, and we call this angle here beta. So if V infinity is coming in from the right wing, that's a positive beta. We've got Y out the right wing, that's this direction here, and then Z out the bottom of the aircraft. Okay, so the forces, the rolling moment, L, is actually a function of alpha and beta. It's not a function of the bank angle. The bank angle is an orientation angle. It simply tells us how the aircraft is oriented relative to the Earth. It does not tell us how the aircraft is traveling relative to the surrounding air. And so this definition here for roll stability just simply does not work. Okay, and that's because this is an orientation angle. Phi is an orientation angle, not an aerodynamic angle. Okay, so we need to define this in terms of an aerodynamic angle. So so roll stability actually is an indirect effect, and actually this is something that's not well understood in the community. Different textbooks have trouble explaining exactly what's going on here. I'm going to follow the explanation of Phillips, which I agree with. I think it's the most straightforward explanation of why roll stability is the way it is, and why aircraft are stable in roll with a certain characteristic here that we're going to talk about. So to understand this, we need to understand one more force on the aircraft, and that is our weight vector. Okay, so our weight always acts down towards Earth. And so what happens is, if we were trimmed for steady level flight here, our lift would have been equal to weight. And if we had some disturbance in roll, so we have some positive bank angle here, now our lift is acting in this direction. It's actually, so it's not aligned with the weight vector anymore. And so because of that, we're going to have two changes. Because of our pitch stability and change in and lift slope of the aircraft, we're going to have a change in angle of attack, because the lift now is not directly aligned with weight. And so that will naturally change our angle of attack. And also, we'll get a change in beta, because the aircraft will begin to side slip to the right, because we have some component of weight now out the right wing. Okay, some component of this force is out the right wing. And before we were trimmed in steady level flight with no side force, right? We were trimmed so there was no side force on the aircraft, but because the weight vector now points out, a portion of that points out in the y direction, we now have a y force that we were not offsetting aerodynamically, and so the aircraft will begin to side slip. Okay, so we'll have a change in both alpha and beta due to bank angle, due to a change in bank angle, all right? And that's the key. So these are the indirect effects. Because of a change in bank angle, we have a change in both alpha and beta on the aircraft. Now, for a symmetric aircraft, the rolling moment is actually not a function of alpha, okay? So this equals 0 for a symmetric aircraft. And this is if it's symmetric, about the XZ plane here, so right to left. So rolling moment does not directly depend on alpha. Now, it could if you had if you were including propellers and things like that, which will affect this. But if we neglect the propulsion system for a moment and just look at aerodynamics without the propulsion system, the aerodynamics of a symmetric aircraft are independent, or the rolling moment is basically independent of alpha. However, the rolling moment does depend on beta. And we're going to talk about the effects of different things on the aircraft, but you can imagine if you have some side slip angle here, that you'll get a rolling moment on the aircraft. Part of that can be due to the vertical stabilizer. Part of that is due to wing dihedral, which we'll be talking about in a subsequent movie or recording here. It can also be a function of the wing sweep angle. Okay, so all of these things, wing sweep, dihedral, the vertical tail, these things affect the change in rolling moment with respect to beta. So what happens is, if we go back to our sign convention here, so a positive bank angle here is right wing down, that creates a force out the right wing due to our weight vector now pointing out the right wing, or having a component in that direction. And so that will increase beta. So positive, an increase in phi creates an increase in beta. And so actually the way we define roll stability is that the change in rolling moment with respect to beta must be less than 0. Okay, that's our real definition of roll stability, is the change in rolling moment with respect to beta. Again, this is an indirect effect. It's actually not beta specifically that we care about. It's actually this bank angle, right? It's for roll stability, we want a change in bank or a disturbance in bank to return us back to our previous bank angle, which, it's easiest to think about that in steady level flight where wings are level, and then you get a disturbance and you want that to come back. Well, that, again, just to recap, the rolling moment is not a function of bank angle. it's a function of beta. And so we need to look at the indirect effect due to side slip, because we'll now have a portion of our weight vector that comes out the right wing, creates some beta. And so so the change in rolling moment with respect to beta needs to be less than 0. Usually we write that as CL comma beta needs to be less than 0. Okay, so that's our roll stability derivative. In order for us to be stable in roll, this change in rolling moment with respect to beta needs to be negative. Now, we can talk briefly about the ranges of this, and you know, the amount of roll stability you want really depends on the pilot and the mission. So for fighter aircraft, they actually don't really want any roll stability. The pilot wants to be in control of that, because if you have too much roll stability, you have difficulty banking, because the aircraft is trying to fight you a little bit as you try to bank the aircraft. And so stunt pilots, fighter aircraft, those types of things, they basically have wings level, or they don't have dihedral in the aircraft or in the wings. We'll talk about that more, but they basically have neutral, what's called neutral yaw stability, which means that CL beta equals 0. So it doesn't actually correct for that. That's left entirely up to the pilot. But for beginner pilots, or for transport aircraft that need or that like to fly basically with wings level and don't want to worry about it as much, then they want to be a little bit more stable in roll, but it does inhibit the maneuverability of the aircraft. And so a kind of a starting rule of thumb, which is really loose, this really shouldn't be taken too seriously, but just as a starting point, you can think that CL beta should probably be between 0 and minus 0.1, okay? The problem is, if you get too far in this direction, this can be really bad. If you get too much roll stability, even for a beginner pilot, if you get too much roll stability, it's really bad. And that's because of the roll-yaw coupling. Because if your aircraft is correcting too easily in roll with respect to beta, remember our yaw stability derivative is also associated with beta. And so now you get this really strong roll-yaw coupling on the aircraft. And so that requires scheduling of the rudder and ailerons really carefully, so you can control both roll and yaw. So anyway, you don't want too much roll stability. This can be detrimental. And also you don't want to get too far in this direction, because that can also be detrimental. So anyway, there's kind of a sweet spot, but again, it depends on the aircraft, it depends on the mission, depends on the pilot, and we'll learn more about that. It also depends on some of the dynamics of coupling between roll and yaw. So we'll get into that more later. Now, the next few videos, what we're going to be doing is trying to estimate the effects of different design decisions on the aircraft to roll stability. How does sweep affect it on the main wing? How does dihedral, how does the vertical stabilizer affect roll stability? The challenge here is that these are very complicated effects, and it's difficult to come up with easy closed form solutions for predicting these various phenomena. And so we're going to be talking more about qualitatively what increases and decreases roll stability, not necessarily pointing out equations so much. Now, on the vertical tail, we actually can come up with an equation for estimating that, but for other things like dihedral and sweep, and we'll also talk about the influence of the fuselage or other stores on the aircraft or on the wing. Those types of things we're actually going to be talking about more qualitatively, and you'd have to really run high fidelity simulations or wind tunnel tests in order to really measure the effects of those to higher accuracy. So, but you'll be able to then look at an aircraft after these discussions and understand why they have maybe placed certain things on the aircraft in a certain way, or how the design decisions of that aircraft are affecting the roll stability.